It doesn't look like much, but there's a lot of work. And then I also picked two problems out of the end of the chapter, 49 and 51. And if you don't have the second edition of the book, they won't be there. But most of you have access to the second edition problem, so if it is a problem for you, let me know, and I'll just print them out for you and give them to you. Make sure when you read the questions, some of them say mechanism, some of them don't say. Most of the synthesis problems don't require a mechanism. Okay? Like the one we just did, we didn't draw any mechanism at all. Okay. Oh, yeah, and there's a bunch of spectroscopy problems at the end. We've already kind of covered the spectroscopy of alcohols, so we're not going to really spend a lot of time talking about it. Okay, but you should do those, and they're required for you to be able to do them. So alcohols have an OH group on it. All right. Lots of alcohols in nature. A lot of alcohols in different kinds of medicinal preparations. You guys are familiar with these because we talked about them last time. I'm going to skip the natural compounds. There's a lot of them. So the other alcohol that's important to know is phenol, and that's an alcohol on an aromatic ring, on a benzene ring. Properties are going to be a little bit different, and we'll talk about that. Why are you guys smiling? Because of the THC? Did your eyes automatically go to THC and recognize?
No, I was looking at the dopamine.
Oh, you're looking at the dopamine? Yeah. You know what dopamine is? Dopamine is like the most awesome neurotransmitter ever. It's involved in like neuromuscular stuff in Parkinson's disease. It's not neuromuscular, but in the motor control. It's all in your central nervous system in the very it's called the basal ganglia. It's like involved in like super primitive things like movement, addiction, happiness. It's crazy. It's involved in so many things. I think it's just one of the really like early neurotransmitters that our body used, or we developed evolutionarily, however you want to say it. And I studied it as a graduate student, so I really like dopamine. I could give you a whole talk on it sometime if you want. I'll just pass over it. But anyways, it's part of what's known as a catechol. They call it a phenol. It is like a phenol, but this is actually known as a catechol. But phenol is that, and we'll learn a little bit about phenol chemistry this semester because it's pretty common that we use it in a lot of stuff. Okay, I am going to skip this for the most part, except I'm going to do one really crazy problem. Okay. Which the book didn't even get the name right. So I thought, this is the one I should do, because this is the one they used for their example that I'm going to do. And then I looked at the answer, and I thought, that's not right. So anyways, I did it. It was fun. So naming alcohols is a lot like naming alkanes. Big difference, you add OH to the end, right? So you add OH, so you add OL to the end of the name. The parent chain is the longest chain with the OH, which we kind of know already, because I've kind of taught this to you before. And that carbon gets priority. That is, you give it the lowest possible number, okay, that the OH is attached to. You list the substituents before the parent, alphabetical order, ignore prefixes. Let's see. Anything else? Yeah, except for iso. We've talked about that plenty of times. The locant, where the OH is, goes right before the suffix. That's the way we're going to do it, okay? You can put it before the name, but I want you guys to get used to putting it right before the suffix, because we're going to deal with some compounds, like the one that we do the example on, where there are two functional groups that have priority. Okay? And then you end up with multiple suffixes. So this is it doesn't look that bad, right? That's the one we're going to name. So we have to decide what the parent chain is. So which carbon, just looking at that, is number 1? the one at the very top, not the one with the OH on it. It's on the longest chain. It doesn't start the longest chain. So number 1 is here. You guys haven't done this for a month or so, so we should just go through it. Some of you haven't done it for like a whole semester and a half. Sorry, guys. All these guys in the front are the ones we canceled on. These are the people, yeah, that should be angry. But they're really nice, I think. I checked my car, air's in all the tires and everything. So. Okay, so that's number 1, and we're going to count through the halogen group, you know, the geminal halides there, and end up down here. And this is 1, all right, 2, 3, 4, 5, 6. So that's number 6 down here. Now, just to say the name, it's 2-all. And it's 3-en, okay? For the alkene. So that's part of the parent name. So if you're naming this, right, you have some choices, but it would be, for example, hex 3-en-2-all. Alcohol has a higher priority than alkene, and so it goes at the end of the name. So this is, I'll give you some variants of the parent name. And the alcohol is at the end because it's higher priority, okay? So you go by reverse priority at the end. You could have also called this 3. This is also acceptable. And you just have to do that because you have 2 functional groups that modify the suffix of the name, and then you just pile the suffixes on the end. Okay? If you had 3 functional groups, the least priority one could have the number in the front, and then the 2 would have to be at the end. So if you had like an aldehyde on here, you would have, it would end in AL, and then all these things would be jammed in there. Okay, now, what else is on 3? 3 is an isopropyl group. So I've taken care of the parent name, so that's this. Either way is fine. So now we have to do this, the other things, the details. We have 3 isopropyl. What else do we have? Anything else? 5-chloro, 5-bromo, right? Not in this order. Actually, bromo would go first, right? But I'm just writing it down. Okay, so when you do the name, ignore all the stereochemistry until you get to the end. There's a lot of stereochemistry stuff that we have to include in here. But we have all the functional groups, all the substituents, okay? And now we just put it all together, and that's the name of the molecule without the stereochemistry, and then we have to incorporate stereochemistry. Okay, so what's the order? It would be 5-bromo, 5-chloro, 3-isopropyl. So I'm actually going to write it all out because your guys are all writing it out. Somebody just walk in? Oh, hey, Ray. You just walk back in.
Walk back.
Yeah. Oh, sorry, I forgot the number. What's the number? 3? Yeah, 3. And then parent name. I'm going to write this goes next to that. Now we have to decide on the stereochemistry. We're almost done. So for the stereochemistry, we have 2 chiral centers and 1 cis-trans E/Z, right? So on 2, if this is 1 and this is 2, I believe. Yeah. And it's going like this. So which way is that? That's S. So we have 2S. And then, yeah, come on, do your thing. And then we have this double bond, just going down in order. What is that? Yeah, no, it should be Z, because if you look at from on this side, right, this is to a carbon, and this is to a carbon with 2 carbons, but this is to a carbon with an oxygen and a carbon, and the oxygen is the tiebreaker. Z, zusammen, means together, right? So that guy is Z, so it's 3Z. I keep doing that. So I'm going to put a comma here, 3Z. And then 6, which is the highest priority, oh sorry, on 5. So here, what's the highest priority? Bromine, and then chlorine, and then this carbon here, right? So it's kind of going like this, right? But the carbon, the methyl group, where the 6 is, right, that's started in the front, right? So you actually have to move that to the back, and so that means it's going to the right. Okay? So it looks like it's S, but since the 6 is the number 6 carbon is not in the back, you have to move it to the back, and when you do that, it becomes 5S. Is it S or? Yeah. So that has to go in front of the whole name. Okay? I'm not writing it all over again. So first thing is this. Second thing is all of this. And the last thing is one of these 2 here. That's the parent. That's the name. I think we just reviewed all the nomenclature we learned last semester in one horrible exam. I like this problem, though. Quite fond of it.
Can you explain why it was Z again?
Oh, Z means together, right? So that means the high priority groups on the ends of the double bond are on the same side of the double bond. So you draw a line here. That's the plane. And then this is This is higher priority than this is. This is a carbon with 2 carbons on it, but this is a carbon with an oxygen and a carbon on it. And this goes by atomic number. So oxygen's a higher atomic number than carbon. So this whole branch has a higher priority than this whole branch. And it's the first point of variation that matters. It doesn't. You don't add it up. You don't say, like what's everything connected to this side versus everything connected to this side. You do like at the first point where it's different, which one has a higher atomic number on any of the branches.
So if there was like a nitrogen instead of
Yeah, well, let's do it like this. Let's say this was carbon, right? But then on this carbon there was an iodine. Okay, then this side would still be higher. Even though these 2 are tied, now you have an iodine at this point. If this side had let's say it was attached to lead, very high atomic. We wouldn't see it probably. If it was attached to lead here, right? Wouldn't matter because there's still a carbon here versus this oxygen. So it doesn't matter total atomic number. It just matters the first atomic number you come across that's different and higher. That's the priority.
and let's say if there's a nitrogen in between the isopropyl, so kind of isopropyl is like
Yeah. So then if this was actually a nitrogen there like this, then that would be higher priority because the first thing you came to is a nitrogen. And it doesn't matter that the other side has more stuff of higher priority. Any other questions? There will be nomenclature, right? Always is nomenclature.
You still like 50% mixing it.
50%. In your mind, you want it to be 50%. It's like 10%, and reactions are like 15%, 20%. Plus all the other like questions with reactions, so it's really, reactions ends up being the whole rest of the test almost. And then there's like 20% of just random theoretical, why is this more stable than this kind of stuff? Okay, so physical properties of alcohols. Hey, look, they have really high boiling points for their molecular weight. Why? Hydrogen bonding. And then chloroethane is higher than ethane. Dipole and dispersion, right? Bigger, easily more dispersive of its charge. So it can be, it's more, we call it polarizability. It's more polarizable, so its boiling point's higher. Okay? So polarizability is important for distinguishing between ethane and chloroethane. And then hydrogen bonding is just so much stronger. If the molecular weights are about the same, hydrogen bonding wins. Okay? So alcohols, because they hydrogen bond, generally are strongly hydrogen bonding to water, and generally small carbon chains. Small carbon chains. What do you think small carbon? That's so vague. What do you think a small carbon chain is? Yeah, probably less than 6. 5, 4, 3, 2, 1. Those are all pretty soluble in water. But basically what happens is the number of carbons goes up. It becomes less soluble because the nonpolar part becomes more important than the polar hydrogen bonding part. And generally speaking, for alcohols, amines, and carboxylic acids, the cutoff is between about 4 and 6 carbons per functional group. So if I add a 10-carbon alcohol, if it's a diol, it might be as soluble as a 5-carbon alcohol. Okay? So you have this hydrophobic region, you have a hydrophilic region, and it's kind of like the combination of those two things which determine its solubility. But generally speaking, more carbon, less soluble in water, less carbon, more soluble in water. More alcohol functional groups, more soluble in water, fewer alcohol functional groups, less soluble in water. So like sugars, right? Like sucrose. Or let's just stick with something simple, glucose. Glucose is C6H12O6, that's kind of the generic formula. It actually has 6 OH functional groups on it. Soluble in water? Yeah, it's very soluble in water. I think the solubility is some crazy thing like 200 or 400 grams per liter. Pretty much what a soda is, I think. Although, just the other day, we were at a memorial for an uncle, anyways, something the Japanese people do like every year, and 3rd year, and 5th year, and 7th year, 11th year. This is actually the first memorial for my uncle. Anyways, they had Snapple iced tea, and I thought, oh, that's got to be, but one of my kids wanted to take a bunch of them. It was a family thing, so they told him to take a bunch of things. Yeah, it's probably better than soda. I looked at it, it's like got 50% more soda than like sugar than soda does. I'm like, what? I said, take 2 and that's it. Man. Sorry. Very soluble in water, that was the point. Okay. So there's a term we use, miscible, right? Miscible simply means mixes in any proportions. So 3 carbons or less generally is miscible. So like methanol, ethanol, propanol, isopropanol, which is rubbing alcohol, all those you can mix in any proportion with water. This is kind of an interesting thing, and I wasn't going to talk about it, and I decided, well, yeah, that's pretty cool, so we'll just leave it in there. This is actually a bacteriological property of alcohols, carbon chain length, right, and ability to kill bacteria. So if you'll notice, like, this is 1 carbon, so that's methanol, There's 2 carbons, that's ethanol. 3 carbons would be like propanol or isopropanol, and then butanol or isobutanol. And you'll notice what happens is it goes up until about this point here, and then it drops down. So the way alcohols work for sterilization is they're able to invade the cell wall and disrupt the cell membrane and like break it apart and get inside and then kill the bacteria that way. So the reason this curve has this shape is these ones, right? Oh yeah, sorry, back up. If you don't know what a bacterial or any cell wall looks like, it's a hydrophilic interaction. There's long hydrophobic chains with hydrophilic parts sticking up on the outside, and we call it the bilayer. You've all heard of that at some point, I'm sure, even in high school or something. But short alcohols can't penetrate the bilayer because they're too polar. Long alcohols aren't soluble enough to be effective, and so that's why out here the solubility is too low, and you can't get enough of the bacterial agent in. And here, it's not soluble enough in the cell membrane, so it can't actually penetrate the cell membrane very well. They give an example. It's actually, I think, the example is for this. And there's a 1, 2, 3, 4, 5, 6 carbon chain. Turns out if the carbon chain's shorter, it's not as effective, and the carbon chain is longer, it's not as effective. That's like they optimize it for being able to go through the cell wall and kill the cell. Of course, I suppose that means is what it does to you, too. I really never thought about that. But, hey. Alcohols are generally can produce conjugate bases of weak acids, or in quote unquote, they're relatively strong bases as their conjugate base. Okay? The way that we can produce the conjugate base, this is the way they show. This is not as common, but you can definitely do this. You use sodium hydride. It's an SN2 reaction of the H- ion attacking the hydrogen, displacing the oxygen, and producing hydrogen gas. Okay? So pretty straightforward SN2 reaction. Actually, the way it's usually done is we do something that's called the Williamson ether synthesis. If you want to see it. This is part of the Williamson ether synthesis. But it's actually a radical reaction. It says show the mechanism for such a reaction. I just showed you the first step of it, right? But the sodium attacks the hydrogen and it cleaves this bond homolytically, and you end up getting homolytic or heterolytic? I always get those two confused. Anyway, homolytic, yeah. So that it breaks the bond. You'll get a single bond between the sodium and the hydride, which that's what that is. And then you can also add a second equivalent of sodium and produce the O- that way. Okay? So it's produced, and the sodium does a couple of different things in there. But you end up with an oxygen radical. The oxygen radical can then be reduced by another sodium to make O-. Then you've also created sodium hydride, and the sodium hydride can reduce an alcohol to make the conjugate base. Okay. Later in the semester, we'll actually make this, and so I'll show you how it's made. And literally, when you do this ether synthesis, or you prepare the ethoxide ion, you just take metallic sodium and you cut it up with a knife, and you just throw it in ethanol, and you keep it kind of cool, and it just bubbles. And the bubbles are the hydrogen gas that's forming. And then what it's leaving behind is this guy in solution. Okay? It's a fun reaction because most of the time you think of sodium as the thing you throw in the swimming pool and it blows up. Or maybe you guys don't think of that. That's the stories I always heard. Like when I was younger. Oh yeah, we used to take like big blocks of that, throw it in the swimming pool, and it would blow up. I'm like, well, why don't we do that? Because it blows up. Apparently it was okay before I was a child. All right, so talk a little bit about the pKa's of alcohols and phenols. Just as a sort of review, right? Alkanes, between 40 and 50 is the pKa. So the conjugate bases of very weak acids. And then if you go down through amines, around 35, 36. Alcohols are between 15 and 18. And then the strong acids and like HF, so like HCl, HBr, HI, those are all in the negative region to -10, and then HF is closer to 3. Okay? So just give you a review of that. Increasing acidity goes this way. Okay, water is right around 15 pKa, so it would be right on this end. It would be about as acidic as the most acidic of the alcohols. By the way, water pKa 15.5 is something you should probably know. Okay, so let's look at ARIO, right? You have cyclohexanol versus phenol. Why is phenol so much stronger as an acid? Has a conjugate base, has resonance, right? So if you look at the conjugate base for this guy, it can delocalize. Oh, it feels good to draw a two-headed arrow again. It can I've been doing these one-headed arrows all the time, and I always have to erase them every once in a while because I keep doing it wrong. It can delocalize into the ring by resonance. Okay. You can make phenols more acidic by adding electron withdrawing groups to the ring. The common example is a nitro functional group. So I'm going to draw that for you over here. Nitro looks like this. Overall neutral, but has that appearance. And just to show you what that looks like, I'm just trying to think if I should draw all. I'm not going to draw all the resonance structures in between. I'm just going to draw what it looks like here. The important one. Like that. That's the important contributor. Overall has a -1 charge, just like this one does. But you notice what happens is by adding the nitro group, it has another resonance structure that allows the delocalization of the charge into the nitro group. Okay? As a result, adding nitro groups into these positions, either here, or it turns out here as well, tend to make phenols more acidic. Okay? And again, in terms of resonance, the features that are important are if you can delocalize the charge, that makes the anion, the conjugate base, more stable, and because the conjugate base is more stable, the acid is stronger. It's easier to produce the conjugate base. Questions? Some review, some new, but it's going all the way back to the beginning of the semester, last semester. So, okay. So if I take sodium hydroxide and mix it with cyclohexanol or phenol, will the sodium hydroxide be a strong enough base, right, to deprotonate the phenol? And how do you make that determination? You look at the conjugate bases, or if you're given the pKa, and that's what I would do, I'd look at the conjugate bases. But if you look at the pKa's, this pKa is 10, and that pKa is 15, and the stronger acid always pushes the equilibrium to the other side. So let me draw that out for you. Draw it something like this. Draw phenol, Oops, actually, you know what I'm going to do is I'm going to make a new slide. Because I'm really out of space on this slide. So you think about the reaction occurring. You can leave the Na out. So this pKa is around 15 and a half. Let's call it 15. And this pKa is around 10. So two ways to look at this. If you're given the pKa's, you're comparing the acid strengths. This acid is able to push equilibrium to the right, and it'll be greatly product favored. So sodium hydroxide, or OH minus, it will be able to deprotonate phenol. If you want to know by what degree the deprotonation takes place, if you remember, the equilibrium constant for this is approximately 10 to the 5th, and you get that by taking the difference between this and this. Okay? So it favors the product side by about 100,000 in terms of equilibrium constants. The other way to look at it, though, is you say to yourself, well, look, this pKa is 15 and this pK is 10, so this conjugate base is a lot more stable than this conjugate base, so that really favors the product side. But you can argue it either way. It doesn't really matter. You could have also, without pKa's, you could have looked at this one and said, oh, this is an oxygen with a negative charge, and this is an oxygen with a negative charge, but this has a benzene ring to delocalize it, so that's a lot more stable. So a lot of ways that you can do this one. I just did the pKa's because I gave the pKa's on the slide. That's like the most direct way. Oop. Okay. What about here? This is in the inductive effect. If you look at ethanol versus trichloroethanol, I guess it would technically be like 2,2,2 trichloroethanol, but trichloroethanol, pK is 12.2, pKa for ethanol 16, right? Why is the trichloroethanol so much more acidic? What's that? Inductive effect of the chlorines pulling electron density away, so it makes a positive, partial positive charge there. Okay. And that helps to stabilize the negative charge when it is introduced to the oxygen, okay, by producing it with a conjugate base. Now, for like comparing all of these, we're going to ignore orbital because they're all on oxygen. And the oxygen orbital is the same for all of them. Right? It's an sp3 orbital usually. Okay. So here's an interesting one. I've heard this explained wrong so many times. So I'm going to tell you like what I learned and tell you why it's wrong. Okay. I probably said this to you like last semester, and this is one of those things you do when you go over writing your notes. You like go and you check your assumptions to see like, is this really right? All right. So my assumption is methyl groups are electron donating, and because they're electron donating, they push a negative charge density here, and when you push the negative charge density here, then it makes it harder for the oxygen to lose the hydrogen, because that produces a negative charge. Okay? So this process is not as strong for T-butanol because, and this is what I learned, all these groups are electron donating. And that pushes a negative charge to this point here, which makes that negative charge on the oxygen less stable. I have believed this for, I don't know, 40 years almost. And then I was reading, and it turns out when you do this reaction in the gas phase, it's the opposite. That is, if you just, this is T-butanol in like solution, but if you measure the energy of this bond and this bond in the gas phase, the trend is actually backwards. It's reversed, okay? And that can't be an inductive effect, right? If it's present in one state versus another, because the methyl groups are always there no matter what. And it turns out it really has to do with solvation. That is, how well the oxygen's negative charge can be stabilized on T-butanol, or the carbon's positive charge can be stabilized on T-butanol, versus how well this charge can be stabilized here and here, okay? So think about T-butanol, it's very bulky, right? And so solvent doesn't have good access to the carbon or to the oxygen just because of the bulkiness of the molecule. So here's the electrostatic potential map, right? In order to stabilize this, you have to put a negative charge on this end and a positive charge on this end. And just because it's bulkier, it can't be stabilized as well. And as a result, it's a weaker acid. Okay? Now, in the gas phase, there are no solvent effects. You separate the molecules from each other, and then the trend reverses. It has strictly to do with bond strength. Okay? So I'll let you think about that. That's a good place to stop. We'll go over this example when we get back and review some of the things we talked about.